Talk about what factors determine an object's resistance. And as you know, the definition of resistance of an object is it is the ratio of the voltage difference across that object divided by the electric current that flows through that object. And the units we use for resistance are ohms. And an ohm is simply a volt per amp. So the resistance would tell you how many volts it takes to drive an amp of current through an object. So what does resistance of an object depend on? Well, it depends on three factors. Resistance depends on what's called the resistivity, which is a property of a material, of a substance, not a property of an intrinsic property of a substance, which does not depend on the size of the object. Then the resistance depends on two other factors: how long the object is, in other words, the distance between the two places where you apply the voltage difference. And then it also depends on the cross-sectional area, A. So if I were to draw a picture here of a cylindrical object, I would apply a voltage difference between the ends of that object. And if this is the higher voltage end and this is the lower voltage end, then I'm going to have a positive conventional current I that flows towards the lower voltage end of that material, and the length would be the distance between where I apply the voltage difference, and the cross-sectional area would be that area right there. Okay, so I
have two materials here. Two objects made of the same material, actually. And these are just carbon paper. So there's a thin layer of carbon here. And this one, maybe you can see, is 21 centimeters long. But this one is 10.5 centimeters long. They're both made of the same material, and they're both the same thickness, and they're both the same width. So they should have the same cross-sectional area because of their dimensions. They should have the same resistivity because they're made of the same material. But one is twice as long as the other, and so you can see, based on our definition, that the one that's longer should provide more resistance. So I'm going to take a meter and I've got it set to measure resistance in ohms. And if I measure the resistance of the long one, I get about 23 to 24 kilo ohms. But if I measure the resistance of the short one, I get about half that. Not exactly. Maybe about 13 kilo ohms. Okay. Now, the other thing I want to show you, here's some more carbon paper. These guys are the same length, but different widths. And they're made of the same material. So which one should have more resistance? The thin one or the thicker one? You can think about that. So the wide one has this much resistance, about 5 kilo ohms. But the thin one has more resistance. It's more like almost 7 kilo ohms. So the idea is thinner materials, which have less of a cross-sectional area, the thinner I make this,
the thinner you make your wire or your material, the more constricted the volume that the current has to flow through, and you're trying to flow it through a narrower area, that causes more resistance to flow. So that's the idea. Alright, so those are the basic things that affect resistance. So different substances have different resistivities, and again, resistivity is a property of different substances, independent of their size, or how long they are, or what the area is. And in your textbook, you can see there's a table that has the resistivities of different materials. So, for example, a really good conductor like copper or aluminum is going to have a very, very low resistivity, leading to a low resistance for whatever object you make out of that material. So these are quite small. Poor conductors like pure water has way higher resistivity. And a true insulator like glass, which is not on this table here, in the units that we're using, which is ohms times meters, glass would have a resistivity of 10 to the 14th ohms times meters. So that's many, many, many times larger than the resistivity of a good conductor like copper. Now there are some materials which are neither good conductors nor very good insulators, and we call those semiconductors. And carbon, which is what I was using in the demonstration, is a semiconductor. And its resistivity is about 10 to the minus 4 ohms times meters. So it would be somewhere in the middle of this table. So you're going to need to use that number in a problem I'm going to give you in a minute. Alright, so going back to the definitions here, let's look at the units. So again, resistance is measured in ohms. Length would be in meters. Cross-sectional area would be in square meters. And in order to make the units work here, you can see that resistivity has to be have units of ohms times meters, because that makes it come out to be ohms. So again, the resistivity of carbon is about 10 to the minus 4 ohms times meters. So it's a semiconductor. Alright, one more thing that you should know for metals is that the resistivity does depend fairly strongly on the temperature of the material. So at higher temperature, if you think about it, whatever this material is, at high temperature that means the atoms will be having random motions at faster speeds than they would at lower temperature. And it's the reason, the ultimate cause for the resistance of a metal is that the current that you're trying to pass through that metal will have collisions. The electrons inside that current will have collisions with the atoms of the material. And the faster those atoms are moving, the higher the temperature of those atoms, the more frequent the collisions of the electrons that you're trying to pass through there with the atoms. And so more collisions would lead to more resistance. So we would expect, for metals anyways, that higher temperature leads to higher resistance, and that was in another page that you should have read. You can see that the resistivity has a linear relationship to temperature, and so T0 would be some reference temperature like room temperature, and rho 0 would be the resistivity at that reference temperature. And then at a higher temperature, if T is greater than T0, then the resistivity will also be greater, because this temperature coefficient of resistivity is a positive number for metals. Because the resistivity increases with temperature, so does the resistance of any object that you make out of that material. It's the same relationship of resistance depending on temperature and resistivity depending on temperature. So I'm going to ask you to do one problem, and that's using the materials that I just showed you. So let's say I had this long piece of carbon, which was 21 centimeters long, and we now know the resistivity of carbon is known to be that value. And we measured the resistance. I'll measure it one more time for you, but we measured it a moment ago. So if I have 21 centimeter length, that resistance was about 24 kiloohms. Let's say it's 24 kiloohms. So your problem is find the cross-sectional area given a length of 21 centimeters and a resistance of 24 kiloohms. Okay, so you should be able to figure that out and tell me the next time we meet in class.